Hello, this is my video for the lesson that we did in class during 1B today, but I had issues with my computer, so I couldn't record at the time. So I'm going to make it now. I'm not in front of the class, which means I will probably go faster, and that if I get to some slide where it says you try, that if you want to try, you might want to pause the video, and when you're done, hit play. Today we're doing graphing radical functions, which is going to fall pretty well in line with the graphing that we did in the last unit. And then I'm going to add just a touch of something from the first section of this chapter, something that I had intended to cover today, but since I'm going to be missing so many students due to a field trip on Monday, I kind of moved a lesson which is a little easier and shorter into today's lesson. And I think we can do that and it won't have any negative impact for anybody. Okay, so you can see here that I'm expecting we're going to test on, I think this is Wednesday. Is that the 18th is the Friday before Christmas, so this is the Wednesday and Thursday we're going to test. Okay, so let's go. So this chapter is about radical functions. And when we say functions, we really mean it's about all things radical. It'll be about radical equations that we solve. It'll be about radical expressions that we simplify and that we add, subtract, multiply, and divide. And it'll be about functions that we graph. And that's what we're doing today. Now, by radical, what do we mean? We mean it's for example, square root, cubed root, could be fourth root, could be anything. And we should recognize this notation right here is pretty much how we transformed the graphs of other functions before this. Right? By multiplying by a number, we stretched or shrank. If the a was negative, we flipped across the x-axis. By adding or subtracting inside the function, we moved it left or right. Minus means right. By adding or subtracting after the function, we moved up or down. Plus means up. So some vocabulary here. The n here, which is in the hook of the radical, is called the index. And we use that word a fair amount. Whatever is underneath the radical, in this case it says x minus h, that is called the radicand. Okay, so those are just vocabulary words that we need to know. The square root function, and although we could do other radicals, we actually only do square roots and cube roots. A square root function has a square root in it. And after we've learned that there is actually such a thing as an index of a radical, we notice that, in fact, we don't have an index in a square root radical. And that is because if you don't see an index, you assume that it means 2. So there's a little invisible 2 right there. Okay, but normally you won't see that. So let me erase it so it doesn't get confusing. Okay, and I just messed that up. So it should have been like this. Okay, now one thing that I didn't put on here that I should is that the square root function has a limited domain. Because as we've already studied in a previous unit, you can't take the square root of a negative number. Or if you do, you're going to get imaginary solutions. And we're graphing this on real number x and y axes that do not support imaginary numbers. So for graphing purposes, we're not taking the square root of a negative number. So we have to take into account that whatever, in this case it says x minus h, but it could be anything, that has to be greater than or equal to 0. Right? So that might leave us somewhat of an equation to solve to find the domain, but it's definitely not going to be all real numbers. Now a cubed root function has an index of 3, which means this is a cubed root, and it doesn't have the same issues with domain. right? Because you can take the cubed root of a negative number. I mean, if you take the cubed root of -8, you get a negative number. It's -2, which means -2 times -2 times -2 equals -8. So there's no issues. There's no issues with the domain of a cubed root function. You know, the cubed root function has a domain of all real numbers. It has a range of all real numbers too, so I mean there's not even much point asking that question with a cubed root function. So the parent functions for square root and cube root functions are the most basic square root and cube roots. So the square root of x and the cube root of x. And this is what their graphs look like. You could determine this yourself just by making a little table of values, right? You could say x and y, you substitute 0 and you would have 0. You substitute 1, the square root of 1 is 1. You substitute 4 for x, you get the square root of 4, which is 2. And all of those points are on this graph. So you see the shape of it. The cube root function, if I did a little table of values, right, x and y, they've got the 3 points there, but -1, 0, and 1. You plug that into a cubed root of x, and you're going to get -1, 0, and 1. If you want to see some, I mean, you could connect all 3 of those with a straight line if you wanted, but we know that that's not the shape of a cubed root function. If we plotted one more point, let's say 8, right, then the cube root of 8 would have been 2. That would have been something about here, right? So definitely a straight line through these points wouldn't come close to a point like 8, 2. So this is the shape of a cube root function. Now the domain of a square root function, since the function starts at the origin and only goes to the right, the domain is x greater than or equal to 0. And the range of the square root function, since the graph starts at the origin and it only goes up, then it's y greater than or equal to 0. Right, so this problem, y equals 1/2 times x, we've done this before and we know what it means to multiply by a number less than 1, right? That is called a vertical shrink. Right, so this is a shrink. What does it mean to us? It means that the graph is going to go up, slower. I mean, what it means literally is that the y values will be of this function will be 1/2 of the y values of the parent function. This is the graph of the parent function. So if the parent function had the point 1, 1, right, 1/2 times the square root of x would have a point 1, 1/2. And it would have a point, instead of 4, 2, it'll be 4, 1. So the graph starts at 0, 0 and it goes like that. Now, did that change the domain and the range? Well, let's see. The graph still starts at the origin and it goes up and to the right from there. So the domain is still x is greater than or equal to 0, and the range is y greater than or equal to 0. All right, this graph is a stretch of a cube root function. Right, it's a stretch because that number, right, is absolute value greater than 1. And you maybe don't be confused with the minus. The minus doesn't determine whether it's a stretch or a shrink. What does the minus tell us? It tells us that this is a flip across the x-axis. Right, so look at this here. The first, I'm going to do this in 2 steps. The first is, if you multiply by a number greater than 1, If you multiply by 3, that means every y value on this graph is going to be multiplied by 3. So here we had the point 1, 1. Okay, now it's going to be the point 1, 3. Right, here we had the point 1, negative 1. So now we're going to have the point, negative 1, negative 1. Now we'll have the point negative 1, negative 3. And it's, again, if I'd have to go out here to 8, and, I normally have the point 8, 2, but I'll have the point 8, 6. In any case, it'll look something like this. Now, that's not what we're graphing because we also have to flip that. But it's starting at that point where my dark blue line is there. Now, if I flip that across the x-axis, it's going to look something like this. Okay, and there you go. That is domain and range are still all real numbers. All the cube root functions will have domain and range of all real numbers. Okay, now we're going to graph some radical functions. And these are not the steps in the book. In the book, they would have you graph the square for y equals a times square root of x minus h plus k. They would have you graph the a times the square root of x. So stretch it, shrink it, plot points, and do all that. And then apply the minus h and plus k. So up, down, left, and right. I don't really see much purpose in plotting points to get a times the square root of x and then applying the h and the k. We might as well just make a table of values at the beginning and then, make it smart, make it a smart table of values, and then connect up our points understanding the shape of the graph. So that's what I'm saying here in terms of our steps for doing this. Make a table of values with 3x values. Make sure that h is one of those values. And then sketch the graph through the points, taking into consideration the graph of the parent function and the effect of all the transformations. So let's see. We should understand the transformations here are flip, stretch, right, up. So 3 to the right, 2 up, flipped. Something like that. All right, now I said let's make a table of values. And I'm going to put h. What is h? Well, it was x minus h in the formula, and this is x minus 3. So 3 is h. Really what it is? It's the 0 of the radicand. And now it'll only make sense for us to put in values of x that are greater than h. We can't put in less, or I'd be taking the square root of a negative number. So how about if I try 3 and 4 first? Let me do those two. Okay, if I plug in a 3 for x, I've got 3 minus 3 is 0. Square root of 0 is 0, which means this whole term is 0. So this is 2. Okay, now let's put in 4. 4 minus 3 is 1. The square root of 1 is 1. Negative 2 times 1 plus 2 is 0. Okay, now try to picture, I said 3 points, 3 values of x. If I put in just because, let's say 5, now I've got 5 minus 3 underneath the square root. That's 2. And the square root of 2 is a decimal. And I don't want to work with decimals. So how can I be smarter about that? Well, I tell you what I can do. I can choose a value that will lead to the square root of a perfect square. And obviously we want to take the smallest one we can. So what if I put in a 7? 7 minus 3 is 4. Now that I can take the square root of, right? The square root of 4 is 2. Negative 2 times 2 is negative 4, plus 2 is negative 2. So that's going to be the pattern. When we do a square root, it'll always be h plus 1, and h plus 4 for our x values. And then you calculate the y values, plot your points 3, 2, 4, 0, and 7, negative 2. Again, we expect this was the parent function, which looks something like that. It was shifted 3 to the right, 2 up, and flipped. And those points look pretty good. So understanding what I'm aiming for here, I'm going to sketch that in. Right now, here's the questions that have stumped in the past, although we did pretty well on what I put on the test, the last test. Right, the domain of this function means what is the set of the x values, right, that make up the points that are on this graph. Well, let's see, they start at x equals 3 and they only go to the right. So how would you say that? X greater than or equal to 3. How about the range? Well, the range, the top y value is 2 and it goes down from there. So how about y is less than or equal to 2? That's it. Domain and range. So here's your you try, and hit pause if you're going to do it, and hit play when you're done. I'm going to describe the transformations. That'd be a good first step. Up.
Please excuse the interruption. Would the student who came by the office yesterday to get his glasses please check by the main office?
Up and, oh sorry, I said up. I should have said stretch. Stretch and to the left. Okay, so let's see, I'm going to take this basic shape, I'm going to move it 1 to the left, and it's going to go up a little bit faster. So table of values, what is h? H is negative 1. Again, that's the 0 of the radicand. And I'm going to put in a 0 and add 4, 3. Okay, let's try those three numbers. If I plug in x equals negative 1, negative 1 plus 1 is 0, and I get 0. If I plug in a 0, I get the square root of 1, which is 1 times 2 is 2. If I plug in a 3, I get 3 plus 1 is 4. The square root of 4 is 2. 2 times 2 is 4. There's my 3 points. Negative 1, 0, 0, 2, 3, 4. So understanding the shape and the shift, that looks pretty good. And the domain and range. I mean, you really can learn a lot about domain and range by working with these square root functions. I mean, you just get practice looking at a graph and just seeing the domain and the range. It's generally something that doesn't come to us easy, but the truth is that once you get it, in fact, it is easy. In this case, looks like the x values start at negative 1 and go to the right, so x is greater than or equal to negative 1. The y values did not actually get shifted, right? That's still at y equals 0, and it's going up from there. So y is greater than or equal to 0. Okay, one more for you. Pause, hit play when you're done. Let me describe these transformations. That is a shrink. That is to the right. And that is down. So, I made this mistake before. This is right 3, down 1. So I probably ought to draw myself and X is about right there. Don't know why I don't have that on there. That will work. Okay, write 3 down 1 and shrink. Make a table of values. I need to have H as the first value. 3. And then I'm going to add 1 and add 4. I think that's similar to the first example. But if I put in a 3, 3 minus 3 is 0. The square root of 0 is 0. So the whole term is 0, minus 1. If I put in a 4, 4 minus 3 is 1. 1 times a half minus 1 is negative 1 half. And then 7 minus 3 is 4. Square root of 4 is 2. 2 over 2 is 1. 1 minus 1 is 0. So let me graph those there. 3, negative 1. 4, negative 1 half. And 7, 5, 6, 7, right there. So here we go. Sketch. Domain and range. Is it coming to you? Should be coming to you more easily. Looks like the domain is x is greater than or equal to 3. And it does have to be or equal. It's going to be a mistake if you just say x is greater than 3, right? You know, that point, 3, negative 1, is the start of this graph. It's not an asymptote like it was in exponentials and logs, right? This is negative 1, so this is y greater than or equal to negative 1. Okay, the cube root function. Again, we know what the cube root function looks like. Something like that. This one has been stretched. It's left. And it is down. I'm going to make my table of values, x and y. I am going to make sure that h is in that table of values. In fact, I'm going to make h is the middle value. I'm going to put 3 values, but I want h to be the middle value. Just because I know the shape, I'd rather have that point and then maybe a point to the left and a point to the right. So let me put in negative 5 and negative 3. So if x equals negative 5, then I'm taking the cubed root of negative 1, which is negative 1. Times 3 is negative 3, minus 1 is negative 4. Right, if h is negative 4, if x is negative 4, then I get the cube root of 0, which is 0. And if x is negative 3, then negative 3 plus 4 is 1. The cube root of 1 is 1. 3 times 1 minus 1 is 2. Okay, let's graph those 3. Negative 5, 2, 3, 4, 5, negative 4. Negative 4, negative 1. Negative 3, and 2. Now, it's very true. You look at those points, so why don't I just connect them with a line? Because you know what the shape of the cube root function is. It's like this. It's not a straight line. If I put one more point in here, I mean, because I don't want to deal with decimals, I would like to have something which is a perfect cube, and that have to be 8. So if I wanted to take the cube root of 8, I'd have to make x 4. Then I'd have the cube root of 8, which is 2. 3 times 2 is 6. Minus 1 is 5. So 1, 2, 3. That would give me a point which is somewhere up here. And then you can definitely see that a straight line wouldn't have dealt with that very well. But let's just sketch in what we can, make the best of the situation, something like that. And domain and range all reals. Here's your U-try. hit pause. When you're ready, hit play. Okay, again, we're doing a cube root function, so we know it looks like this. It's being shifted down 5. Table of values. What is the value of h? 0. Right? There's no plus, x plus a number, x minus a number inside the radical, so it's 0. -1 and 1. So if we put in -1, the cube root of -1 is -1. Minus 5 is -6. Right? The cube root of 0 is 0. Minus 5 is -5. The cube root of 1 is 1. Minus 5 is -4. And if there's room on this, I'm going to put in 8. Cube root of 8 is 2. 2 minus 5 is -3. -1, -6. 0, -5, 1, -4, and 8, 2, 3, 4, 5, 6, 7, 8, -3. So just doing that little piece right there, and it looks something like that. And of course it's symmetric. It should look about the same on this side. There's your cube root function. Domain and range, all real numbers. Okay, one more time. This one has been hit pause. When you're done, hit play. This is the flip. Left and down. So we would expect we're going to take this shape, we're going to flip it, and we're going to move it left 2, down 3. So somewhere down here. So here's my graph, or here's my table of values. H will be my middle value, -2. Then I'll put in -3 and -1. And I guess I would need to have 6 on here to do another. I'm going to do that. I'm just doing that so it doesn't look like a straight line would meet the points. -3, the cube root of -1 is -1 times negative is +1 minus 3, -2. -2 plus 2 is 0. 1 plus -1 plus 2 is 1. The cube root of 1 is 1. -1 minus 3 is -4. And 6 plus 2 is 8. The cube root is 2 with a negative in front of it. That's going to make that -5. Let's plot all these points. -3, -2, -2, -3, -1, -4, and +6, -5. So we're looking for a shape that's something like that. Let's see if I can do this. Not bad. Okay, then I'm going to, that is the end of our graphs of radical of functions, which is to us square roots and cube roots. Now I'm going to talk just a little bit about radicals and rational exponents, because in fact that's two different ways to represent a radical, and we need to know how to use rational exponents. So if you haven't seen this before, we know that you can multiply the square root times itself. And for this example, the square root of 2 times the square root of 2 is 2. But using the properties of exponents, it's also true that 2 to the 1/2 times 2 to the 1/2, you add the exponents, that's 2 to the 1, which is 2. So these are the same thing, which means that the square root of 2 equals 2 to the 1/2. Right, that's just two different ways to write it. 2 to the 1/2 means the square root of 2. Or the cube root of 5, right? The cube root of 5 times the cube root of 5 times the cube root of 5 is 5. Well, also 5 to the 1/3 times 5 to the 1/3 times 5 to the 1/3 is 5 because you just add the exponents and you get 1/3 plus 1/3 plus 1/3 is 1. So the general rule is a, that's just a number, to the 1 over n fraction is the radical of a with n as the index, or what we call the nth root.
Good afternoon, Tabb.
So again, a radical with an index of n is called the nth root. It's just the general way to say a root, right? Now take, for example, if I'd had the 4th root of 7, by what we learned on the last slide, that would be 7 to the 1/4. Now I'm going to cube both sides. 7 to the 1/4 cubed is 7 to the 3/4, because properties of exponents tells us that we multiply those. So that tells us 7 to the 3/4, that's rational exponent, is the same thing as the 4th root of 7 cubed. Or, here I raised 7 to the 1/4 to the 3rd. I multiplied the exponents and I got 3/4. But I would have gotten 3/4 even if it would have been 7/3, 7 to the 3rd, to the 1/4. It's still a multiply between these two. So these two are the same. But this is slightly different. That changes that 3, which was the exponent, outside parentheses is now inside. But it's the same thing. It's the same thing because of this, right? Because of this, that is the same thing. Rest assured, it is the same. So this is our, kind of not exactly what I hoped it would say here, but a to the m over n equals the nth root of a to the m. And what I just said is that's also the same thing as the nth root of a to the m. So the power can be inside the radical or it can be outside the radical. And this is just showing you that if you have it to the negative fraction, well, then you need to flip it to the denominator and then do the same thing as we did up here. So I'm going to do one of these, and then you're going to do one, and then we're going to do those for homework. I think I'll start with number 8, right? And this is an SOL. We're supposed to be able to take something that's written in radical form and write it in rational exponent form. So this would be 8. It's going to be raised to a fraction power. Okay, we know that the index is the denominator. And in this case, it's a 1 in the numerator because there's no powers involved. Okay, you try number 10. If you want to pause, go ahead and pause. This one is very quick. This is 15 to a fraction power. The index is the denominator, and there is a power involved. It is a 3. So that's going from radical form to rational exponent form. Okay, now we're going to go the opposite direction. Again, I'll do 12 and you can do 21. Okay, this is going to be a radical. The index of the radical is the denominator. And there's no powers involved, so it's just the 3rd root of 7. Okay, you can pause now while I do number 14. 21 raised to a fraction exponent. The denominator is the, start this again. We're trying to go to a radical, that's right. The denominator is the index 4. The power can be inside, or it could be that you write it like that. Either one of them is the same. Sometimes it's more practical to do one over the other. And that's it. Graphing radical functions, that's the homework, and I will see you next week.